Alright, so elimination reactions. We're going to see that just by altering some reaction conditions, you can cause the same reactants to form completely different products. Okay, so for example, as we've learned before, if we have a dilute aqueous sodium hydroxide solution, the hydroxide ion is going to act as a nucleophile, and a substitution reaction is going to occur to produce an alcohol. So the hydroxide subs in for the bromide, end up with the alcohol and a bromide ion. If we change the reaction conditions though, and we use a hot alcoholic sodium hydroxide solution, that is sodium hydroxide dissolved in ethanol, we're going to get an elimination reaction with an alkene being formed. Okay. So what ends up happening really is you're going to have these two come off. That hydronium is going to react with the hydroxide to form water, and then your bromide ion is going to be in solution, and you're going to create this alkene. So just by changing the conditions, I form a totally different product. The second reaction, hydroxide, acts as a base. Okay, elimination of the hydrogen bromide can proceed either by a carbocation or by a concerted process. So, if I have, this should be a tertiary, or it could be a secondary, but to make it clear, let's make this a tertiary. So that's a CH3. So tertiary, this bonded pair of electrons is going to come to the bromide. It's going to form my carbocation with the bromide ion. Your hydroxide is going to pull off this hydrogen. The bonded pair between this carbon and the hydrogen is going to go into the bond between the two carbons. This lone pair of electrons is going to be donated to the hydrogen. It's going to form water. This lone pair, or this pair of electrons going in, is going to form that second for that double bond, forming the alkene. Or we could have a concerted process where this lone pair is going to be donated to this hydrogen to make water. This bonded pair is going to come between these two carbons as an additional bond. The bonded pair existing as a bond between this carbon and this bromine is going to go to the bromine, making the bromide ion. Okay, the products are the same, it's just the mechanism is different. And you can't think of it as being, if I would have an SN1 mechanism, the elimination can be referred to as an E1. I have an SN2 mechanism, I would then have an E2. All right. Remember this being the carbocation, unimolecular, the SN2 being a bimolecular. Right, now, hang on, let me get rid of my... So, eliminations reactions of the halogenoalkanes. Okay, in the presence of ethanol, there's also going to be some ethoxide ions present. This ethoxide is a stronger base than the hydroxide, so that the equilibrium is going to lie to the left. But some of those ethoxide ions will be present, and they might actually be the substance that is actually acting as the base. Right? Need to know? I don't know. Kind of interesting, I guess. Alright, let's move on to condensation reactions. Reactions between two molecules to form a larger molecule, and it's going to eliminate a small molecule, typically water or hydrochloric acid. So for example, let's take a look at an alcohol and a carboxylic acid. Okay. The carboxylic acid and the alcohol, ethanol. These two are going to react to form the water, leaving behind the ester, C double bond O with the O to another R group being the ester. Okay, hopefully you can see how that would happen. To me, these two things leave, and then the other two things join together, and it makes an ester. Okay, thing to note, esters have distinctive, pleasant, fruity smell. They are used as natural and artificial flavoring agents in food. They are also used as solvents in perfumes. They're used as plasticizers, and those are substances that are used to modify the properties of polymers, making them more flexible. Okay, and the reason why they are pleasant, fruity smelling and you can smell them is because the IMFs in an ester is going to be much lower than in an ethanol or the ethanoic acid. Since I have a bond in the molecule of an oxygen to a hydrogen, and here a oxygen to a hydrogen, this means that this oxygen is partially negative. Okay, and remember, because of the electronegativity of that oxygen, it pulls this electron cloud really this way. So this is almost a full plus. Very attractive to other molecules alongside of it, and it'll form those hydrogen bonds with those other molecules, strong IMFs. In the ester, I do have dipole-dipole, but I don't have the stronger IMF hydrogen bonding. So these are more volatile and hence the use as perfumes and additives to foods. Okay. So, a lot of times it's useful to show a general reaction for a carboxylic or for any type of reaction. And if you remember, the R just stands for a chain, a carbon chain, an organic compound. If I want to show two different ones, I use things called prime. If I had reason to show a third one, I would use R double prime. Okay. So what this allows us to do is really kind of focus on the reaction that we're concerned with, and that is the one between this carboxylic acid and this amine in this particular example, where these two parts of these two functional groups bond, forming water, and then I will form an amide. So carboxylic acids and amines come together to form amides. These are important in biological systems. Amino acids contain an amine group and a carboxylic acid group. These amino acids can condense together in the presence of enzymes, and they form polyamides. I can form really long chains as long as the reactants contain two functional groups. So they contain a functional group kind of on either end, and it allows them to continue that chain and make this big long polymer. And this is essentially what it would look like. If I have benzene 1,4-dicarboxylic acid, I have a carboxylic acid group on both sides of this molecule. For an ethane 1,2-diol, I've got an alcohol group on either side. That lets these combine, and then this side can combine with another carboxylic acid. So it can make a repeating unit and be called, because these are esters, can be called a polyester, meaning many esters. Okay. Same thing here, got the carboxylic group with an amine group coming together to form an amide, and it can keep going on either side. This is a nylon 6,6, and it's because each carbon chain here contains 6 carbon atoms. and then the next we'll talk about pathways.